everybody, my name is Suborno Isaac reading from NYU, and today we'll be solving the Basel problem. Alright, so what even is the Basel problem? Well, let's talk about the squares. So 1, 4, 9. What do you?
Basel problem is it?
Yeah, that's what I'm about to show. So this is the sequence of square numbers, right? Right?
Yes.
Alright, so now let's invert them. So 1 over 1, comma 1 over 4, comma 1 over 9, comma 1 over 16, comma 1 over 25, etc. If you have experience in engineering or something like that, you probably already know the decimal values of all of these. So just like so, 1 over 16 is pretty sure it's this. 1 over 25 is this, so on and so forth. Now, the problem we're trying to solve here is this is the sum of the inverse squares of every positive integer. What happens if we sum them all up? This is an infinite sum. So now, people in the 1800s calculated this and ended up with approximately 1.644. But they wanted an exact value, and Euler gave them that. In fact, the Basel problem is named after Euler. Indirectly, though, because they didn't want to name something after Euler for the 700th time. Euler was actually born in the Swiss city of Basel. However, it's also named the Basel problem for one other big reason. The Bernoulli brothers, who both unsuccessfully attempted it, I'm so sorry to both Jacob and Johann, both of them unsuccessfully attempted it, and both of them were born in Basel as well. So, that's...
Dumb brothers.
So, that's why it's called the Basel problem. So, the thing is, this is actually... Oh, not that. Pi squared. This is the epitome of weirdness. Why is pi here and why is it squared? Oh, that's the exact same thing 3 Blue 1 Brown asked. So, this is actually for a very interesting reason. So, in the full lecture, we're going to talk about...
Can you push it more? Can you push it more and instead something,
In the full lecture, we're going to talk about deriving the Weierstrass factorization theorem. Or I can write it like this. All you need to know about it right now is that it allows us to derive an infinite product form for any function. So, given any function f of x, we can then express it as an infinite product of some function of x. So, it might involve other variables too, like n, of course. So, in this case, what we specifically want to do is we want to have this expansion for sine pi x over pi x. And it turns out this specific expansion is actually the infinite product of 1 minus x squared over n squared. Strange, right? So, what we're actually going to do here, first of all, is we're going to unite this, make a common denominator right over here. So this is going to be n squared minus x squared over n squared. And then we have sine, oh wait, no, we don't actually have to do that. And then we have sine pi of x over pi of x. So first thing we do is differentiate that. Wait, no, that's not the first thing we do. Infinite products are notoriously hard to deal with. And besides, the thing we were talking about earlier was the infinite sum, not the infinite product. So, how can we convert from a product to a sum? Well, luckily, logarithms have us covered. for some reason, the source I'm using uses natural logarithms, but I don't think it really matters what you use. Oh wait, it does, because using natural logarithms gives you this nice formula. So, the nice thing about it, is that the natural log of a times b is equal to the natural log of a plus the natural log of b. Core property of logarithms right there. So then, if we use this infinite product, then it can be converted into an infinite sum. So ln of this infinite product is equal to the infinite sum of ln of this. Alright, cool, right? So then, what are we going to do now? Well, we are going to differentiate on both sides with respect to x. Alright. And that is going to be pretty useful, because then what do we get from this one? Well, we have to use a little bit of the quotient rule right there. So sine pi x over pi x, we get the derivative of the top, we gotta add the pi, times the bottom, minus the derivative of the bottom times the top over the bottom squared. So then I'm just going to cancel out this to give us pi x cosine pi x minus sine pi x over pi x squared. Pretty sure that's right. Alright, and then what we're going to do is on the other side, we have, the thing about it is you can actually interchange these series by something we'll cover in the full lecture. I believe it's called Tanner's theorem. So this is equal to the infinite sum of the derivative of whatever was there in the first place. So then that actually gives us something pretty cool. All we have to do is take the derivative of this with respect to x. So what's that going to be? Well, we have ln, so we do this first. And then by the chain rule, we multiply it by minus 2x over n squared. So then we get minus the sum of minus 2x divided by n squared times, what is this? This is n squared minus x squared over n squared. So doing this gives us n squared over n squared minus x squared. So we get cancels right over there. Alright, cool, right? So now we're going to divide both sides by 2x. This is a dumb move. First of all, because...
Oh, you can use the rate whenever necessary.
Yeah.
As I glorify my physics with it.
I accidentally didn't put the ln on this, which makes things a lot easier. And that's the intended route to go. So this is not the true derivative. And second of all, that means that we don't have to use the quotient rule, because by the properties of logs, this is actually just reduced to a subtraction. And then we want to do d dx of that. Now, what is that? Well, that should be pretty easy. What's this part, first of all? Well, it's 1 over sine pi x. And then on the top, we get pi cosine pi x. Now, this is just going to be reduced to pi cotan pi x. And then we subtract ln pi x. So that's just going to be 1 divided by pi x. times pi. Yes, times pi. So there we go. This is what we get on the other side. So then this is equal to the same thing that we stated above. And we're actually going to use this to flip the denominator. Then we're going to divide both sides by 1 over 2x to get pi over 2x cotan pi x minus 1 over 2x squared is equal to the infinite sum of 1 over x squared minus n squared. All right, good. So now here is where we're going to do a very important step. We're going to substitute x for it. And yes, the I here stands for the square root of -1. T is just the variable my source likes to use. So this is going to be how we solve this problem. So now let's plug in x into it immediately and see what it gives us. Pi over 2it cotan pi it minus 1 over 2x squared is going to be 2I squared t squared. So that I squared is going to make this positive. And this is equal to the infinite sum of 1 over I squared t squared, which is going to make this minus t squared minus n squared. So then we can actually flip the signs just to make this nicer. Yeah, okay. So there we go. That's everything substituted in. So now we're going to have to do something very interesting with hyperbolic functions.
You made negative. You put negative positive. How?
Well, this was minus minus before, and this was all plus. Then we just switched everything. So, all right. So now we're going to harness the interesting properties of hyperbolic functions. So the thing is, sine 8 to the ix is actually equal to e to the minus ix plus e to the ix divided by 2. And this is equivalent to I sine of x. Meanwhile, cos of x, I cos of x, is equal to e to the ix minus e to the minus ix over 2, which is the same thing as cosine ix. If we divide this by this, we get cos of ix is equal to 1 over I times cot x, or cotangent x. Now 1 over I, as you should know, is I cubed, or negative I. So this is a relation that we can use. Now, when it comes to this, we actually have cotangent of pi it. So let's plug that in. So minus I cotangent pi it should be equal to something like cos times pi I squared t, or minus pi t. Interesting, right? Now we can simplify this a little bit because we know that cos x is equal to, one second, we just got to make sure. It's always beneficial to make sure in these cases. Yeah. Cos x is equal to cos minus x. Meanwhile, sin of x is equal to minus sin of minus x, which means that cos of x is equal to minus cos of minus x. Good. So that means that we can remove that right over there, and we can place that over here. So, yeah, all right, that's right. So then I'm just going to cancel out these negatives, and boom, we've got something cool right over here. Now, let's see how that compares to this. Now, right over here, we see that we have pi over 2t times negative 1 over I. Now, turns out the negative 1 over I is just I cubed, or negative I, so then multiplying a negative by a negative grants a positive, pi over 2t times I. So then, that means this acts exactly like how we want it to. So let's bring everything from here over down there. So we get pi I... No, I need this space desperately. So we get pi I over 2t cot pi I t minus 1 over 2t squared is equal to that infinite sum of 1 over t squared plus n squared. All right, that's good. So this is what we have so far. Then we're going to plug in our value right over here for cos of pi t. So we get pi cotangent hyperbolic it divided by 2t minus 1 over 2t squared is equal to this. Now, I'm going to keep the long story short. Wait, did I write cos it? I meant to write cos pi t. I'm going to keep the long story short over here, because you really don't want to know the long part. So, all we do over here is we repeatedly use L'Hopital's rule. So first of all, we make a common denominator. So pi t cos pi t minus 1 over 2t squared is equal to that. And then we just use L'Hopital's rule over and over. Specifically, we set the limit as t approaches 0 on both sides. Now, this doesn't work as is, so we take the derivative. The derivative is a hellish nightmare 4 times in a row, but if you want a hint on how to actually proceed doing it, if you don't want to use a calculator, well then you have to simplify cos pi t into e to the 2 pi t plus 1 over e to the 2 pi t minus 1. So you use it repeatedly and repeatedly until you get a polynomial expression where you can actually just plug and chug is equal to the limit as t approaches 0. We absolutely don't affect anything over here at all. So once we plug and chug, we get that this is pi squared over 6 is equal to the sum of the inverse square, pi t plus 6. That's what you get when you do all the plug and chugging and apply L'Hopital's rule 4 times. So the limit is t approaches 0. I'm just doing this to give you a satisfying solution instead of saying blah 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 pi over 6. So then once you plug and chug, you get that this approaches 0, this goes to 0, and this goes to 0. And you're left with pi squared over 6. There it is. Alright, so today we solved the Basel problem using the Weierstrass factorization theorem. And the most important part was probably this t substitution of x into it at the end. And additionally, this substitution of the circular trigonometric function for a hyperbolic trigonometric function, which allows us to substitute this in for a very not nice derivative for L'Hopital's rule. Then we just apply it over and over until we get something where we can actually plug in chug, which is what this shows. This is where we can plug in chug. Then we get this, and we get pi squared over 6 is equal to the sum of all the inverse squares. That's the summary. Thank you for watching.